Very good. Well, welcome everyone to this presentation. I'm Martin Fernø, professor at the University of Bergen at the Department of Physics and Technology. So today I will be talking about the UiB FluidFlower concept for CCS. And I will talk about the concept as it is, some of our research activities, and I will also show you what will happen in the subsurface in one of the demonstrations here. I want to start out by saying that this is a collaboration between researchers across 3 departments here at the Faculty of Natural Sciences and Technology. So I'm at the Department of Physics and Technology, and then also we have very strong collaborators at the Department of Mathematics and also from Earth Science. At UiB as a whole, there are numerous departments and researchers working on CCS, which is carbon capture and storage, from social sciences to regulatory framework and so on. So it's quite a broad activity. So just to set the scene, we are about to launch the Longship project, which is this large Norwegian full-scale CCS project supported by the Norwegian government and also industry partners, where they're capturing CO2 in close to Oslo from a cement factory, transporting it via ships to our neck of the woods here in Bergen, out at Øygarden, where it's the receiving terminal, and then there's a 100-kilometer pipeline along the seabed out to an injection point that goes 2.6 kilometers into the subsurface, where the captured CO2 is permanently stored. So for this presentation, we are focusing on the end stop of the CO2, which is basically the subsurface reservoir. And as you can see from the inset here, Bergen is down here, and then Øygarden, and then that's the pipeline out to this injection well out in the North Sea. So going 2.6 kilometers in the subsurface, it's kind of hard for us today, but we and also our research, but we build models to understand this the displacement process when you inject the CO2, and also these trapping mechanisms. And that leads to this FluidFlower concept, which is basically summed up in this slide here. You can see the large FluidFlower. We have several large, medium, small. The large FluidFlower in where you have people standing in front, so you can basically build a physical representation of the subsurface, and you can do a range of things. And we said that we're connecting the dots between research, innovation, dissemination, and also STEM recruitment. So I will touch upon some of these issues today. So FluidFlowers are, you can see the pictures here, basically in some sense an accessible and immersive carbon storage experience. You can stand in front of this, you can see what goes on with your own eyes. And we utilize this infrastructure, which it to many degree is in interdisciplinary research and education, public outreach, energy transition, and we're also use this actively in continued learning courses for the industry. Now we can set up as an experiment. We call it a multi-physics room scale experiment, and we are able to represent the complex geology in the subsurface. You can see the blue and yellow picture is actually representing a seismic profile out in the North Sea, but in a physical model in the lab. So we can also reuse the same geometry over and over again, so that we can do parametric studies, and that we use to verify modeling codes and also evaluate these injection strategies, because that's the key. You have to know how to best optimize your CO2 injection to maximize storage potential and minimize leakage risk. One of the activities that we've done a lot on is outreach and dissemination. I'll just show you this one slide on that, where we either do museum exhibitions, we have kids-focused activities where we bring these small fluid flowers out and about, and kids get to build their own reservoir and inject CO2. And we also go around with this traveling kit and show people the subsurface processes that are important for CO2 storage. So that's been quite successful. We just last week had a big event in Larvik, this climate summit, as one example. What I want to talk about now is the research, and this slide basically sums up about 3 years work, or 2.5 years of work in what we label the FluidFlower International Forecasting Study. I'm not going to go into details about how we set up the study. We just published last year, a special issue in Transport and Porous Media about this, 15 papers. But the idea was to do a double-blind study where we provide a physical ground truth from the lab. I'm an experimentalist. And then we invite the modeling community within carbon storage to forecast blind what will happen in the experiment. And they all utilized their own simulation tool. So that mimics actually what you do it mimics the process of what you need to do if you want to do that at industrial scale, but you don't have a physical ground truth before you start. So in some sense, we had the sort of true answer in the physical experiment. And what you see here is the physical experiment in the center, and I will actually come back to that. I will show that video. That video was not seen by the participants. Here there's 8 participants which provided their forecast. You do not need to know much about numerical simulation and reservoir simulation and modeling, but you can see that these snapshots in time of distribution of CO2 in the model are not the same. So all of them have the same information, and they solved this forecasting study differently, and there's a quite a lot range of forecasts here. So that can tell you a couple of things. Number one, this is not a straightforward problem. And number two, you need to take quite care of how you set up the model and what physical processes you include in that. So again, I don't want to try to summarize those 15 papers here in a minute, but the take-home message is that this is quite difficult to do. And one of the things that was difficult was because they didn't know how the physical ground truth was. So I will just start this video. So what you see here is actually a time-lapsed video of the experiment, where the experiment is mimicking a synthetic subsurface reservoir where the CO2 is trapped. We have a lower reservoir down here at the bottom, overlain by a low permeable seal, and that seal is broken off by a fault structure here at the bottom. And then we have between the top seal here, there is a more finding upwards sequence. Basically means more heterogeneity, more different sands there compared to the lower reservoir, which is homogeneous. So I'll just start the video, and what you will see is CO2 being injected and how the CO2 flows into this porous media. All the physics in our lab experiment are also present in the subsurface, let's say at the Northern Lights project. So the displacement here and the physical mechanisms that we observe in our lab is the same as we will see offshore. So what you can imagine now, we've started the injection. The CO2 comes in as a reddish color here. It's buoyant, so it flows up, and then it migrates along the seal. Then we start the injection in the upper reservoir while keeping the injection in the lower reservoir. Now we keep injecting until we sort of fill up the trap below, and it spills over this spill point at the left side. And now we have stopped the injection. And now you can see that the heterogeneity in the geological units here dictate how the CO2 is flowing. If you can see, you have a trapped gas sitting here on top. So this is buoyant gas of CO2. And then this red color is actually CO2 being mixed with the water, so-called CO2 saturated water. And that has a different color and a different density. So it actually is sinking towards the bottom quite slowly here. So now we're about 11 hours in. And we run this for about 5 days. Now, then we repeat the experiment so that we can look at a physical variability between runs, so that we can actually quantify how similar these things are in the lab. And turns out they're very, very similar. And you can see now that this CO2 is sinking as it is going into the aqueous phase. Let's see if I can just advance the slide. Here, I want to show you a different example. This is a different geometry. This is actually taken from a seismic image, which I alluded to in the start. We also flipped out the color scheme here by basically using a different set of pH indicators. And I've included this because we also speed up time here so that you get this convective mixing, which is a quite important phenomenon. Again, we start down here, the CO2 is injected, it's buoyant, it goes up, it touches this first low permeable streak, flows along. So geology is obviously very important. It moves up here, and there's a lot of physics in how these displacement occur. And it goes up to a sealing structure at the top. We start the second injection, slightly different behavior here, but overall quite similar. And you will see now it's about 3 hours in. And once we've stopped the injection, you can see on the time it's starting to speed up very soon. And then you will see something quite interesting here. As we now speed up time, the CO2 is dissolved into aqueous phase, which becomes more dense and actually starts sinking. So what you're seeing here is sinking away from the seal structure and actually going down towards the bottom. Now we're 3 days in, by the way, so it's quite rapid here. And that means that the leakage risk is reduced. Now we are resetting the experiment. So we flush everything out. This is a lab experiment. We fill it back up with blue, and then we can redo our experiment either on the same well pair or different well pair. So that's basically how we utilize this. I would also like to touch upon something that we are currently doing, and later this month this will be presented at the Reservoir Simulation Conference in the US. So we set up, based on our academic study of the FluidFlower benchmark study, we set up a more rigorous simulation study, a so-called comparative solution project. It's called the 11th SPE comparative solution project. There's been 10 before, but that was the last one. Number 10 was around over 20 years ago. And this is the first one since that, and also the first one on CO2 storage. So we set up a quite difficult simulation program, simulation problem, and invited industry, commercial providers of numerical tools, and also academia to try to solve this. We had a lot of interested parties, and we spent the better part of a year on this. And now we have the results, we have analyzed them, and we are now publishing this later this month. And we believe it's an important step and a common platform and reference case for how to best simulate geological carbon storage and the tools needed to do this with a small or a very small degree of uncertainty is, we need to improve those tools. Most of the tools are to some degree inherited from the oil and gas activities and tweaked to do CO2 storage, which is basically the opposite, right? So you eject carbon rather than produce carbon. There is a lot of new or specific CO2 physics, let's say, that needs to be added to these models, and this really highlights that effect. Lastly, I want to emphasize that this concept, the FluidFlower, is not only happens in Bergen. It was sort of born in Bergen, but research is international, also interdisciplinary. So these circles around the globe here highlights the fact that all of the white rings are research collaborators, and where we have the red rings is where we have placed FluidFlower rigs, physically placed them. So in South America, in North America, in Europe, and also in Australia, where they have now FluidFlower is built here in Bergen, placed in their location where we collaborate on research and dissemination activities. And without going into too much detail about the logos here, you can see that we are collaborating with a broad range of leading academic institutions and also industry partners. So I think that's it. So thank you so much.